Nice. Fine.
Good evening. Can you hear me?
Yeah, no, you're good.
Okay. Good evening, everyone. Welcome to Cafe Scientifique, brought to you by the University of Victoria, Faculty of Science. Before we get, can you turn it up a little bit? They're having trouble in the back. Is that better? Okay. Before I introduce the speaker for tonight, I would just like to acknowledge and respect the Laporgan speaking people on whose traditional territory the university stands, and the Songhees, Esquimalt, and Wasanish people whose historical relationship with the lands continue to this day. The speaker for tonight is Dr. Mariya Goncheva. She is an assistant professor in the Department of Biochemistry and Microbiology in the Faculty of Science at UVic. And I'll give you a little bit of her history. She did both her bachelor's degree and her PhD from the University of Edinburgh. And then in 2017, she made her way to Canada at Western University, where she did her postdoctoral fellowship. Then she was out on the job market, and she was the successful candidate for a CRC chair here at the University of Victoria. And so that's a chair in virology. And her lab has really been building in momentum. And the research area is in looking at co-infection between viruses and bacteria, and the, I guess, negative outcomes by a co-infection. She's been here since 2022. She's very energetic. She's just a pleasure to have in the department. And she has lots of interactions with students, and she's truly a rising star in the research landscape of Canada. And so please join me in welcoming Dr. Mariya Goncheva.
Okay, good evening, folks. Everyone can hear me at the back? Awesome. Thank you, Jen, for the fantastic introduction and for the invitation to be here as well. Thank you all for taking the time out of your Tuesday evening to listen to me talk. As Jen said, my lab studies viral bacterial co-infection. So I hope that what I can do today is tell you a little bit about both of the pathogens that I study, so influenza viruses and bacteria, a little bit about our lungs and respiratory system, and really how all of those four things come together in the end. So as Jen mentioned, I've been in Canada since 2017. I moved for my postdoc, but I want to tell you a little bit about my grad degree, because that was really the start for me of my fascination with co-infection. So I did a PhD at the University of Edinburgh, and my PhD topic was on co-infection between influenza A virus and Staphylococcus aureus. And the project kind of pivoted within the first 3 months of what I was doing. So really, I signed up to do one thing and ended up down another path. But that path has stayed with me ever since. When I moved to Canada, I moved for a postdoc to study the pathogenesis of Staphylococcus aureus. Many of you have probably heard about Staph aureus as MRSA or MRSA, which is the drug-resistant version of the bacteria. It's a really big problem in hospitals and causes a variety of diseases. And because I'd had so much experience with flu in my PhD, I was like, I'll come for a postdoc, I'll study bacteria, I'm going to diversify a little bit. Like, this is going to be really cool. And then March of 2020 happened. Now, nothing significant happened at that time at all, so I probably should explain a little bit about what this is. But I was at Western University in London, Ontario at the time, and Western had quite surreptitiously just certified their level 3 lab a month before the pandemic was announced. So when the pandemic happened, then all of you in lockdown for 2 weeks. And then I went back to the lab because I was one of the very few people that actually had, it's like, well, you know, I know about viruses, I know about respiratory viruses. Yes, this one's different, but I have some skills that can hopefully contribute. So I spent 2.5 years of my life in a containment level 3 lab studying COVID, you know, in a full spacesuit, away from everybody else and incapable of communicating with anyone. It was really peaceful, okay? It was joyous. Kind of wish I still had that sometimes. But really, my ability to go and study COVID kind of reignited my desire to continue doing co-infection, because clearly this was a problem beyond just the flu and other respiratory viruses as well. So I've kind of embraced this idea of studying co-infection as a really important clinical problem, and a really difficult one to address in the lab because, as I'll hopefully tell you, it's quite complicated. So I want to give you a bit of an introduction to us as humans and our respiratory system, and to my 2 favorite pathogens, and how this relates. Okay, so our respiratory system, our lungs, are obviously a major organ, right? But actually quite special. They're a little bit different to every other major organ because their job is gas exchange. We take in oxygen, we exhale carbon dioxide. But in order for that to happen, our lungs need to actually be constantly exposed to the outside environment. So yes, you're breathing in air, but in that air, there's dust, there's viruses, there's bacteria, there's pollen that you're allergic to, there's random fumes from cars, and, you know, really everything else. So your lungs are a system that needs to be constantly open so that you can take in oxygen, but that in itself is a really big challenge, because then you're also constantly trying to get rid of all these things that you don't want. So that is quite difficult. And the lung has adapted in many different ways to facilitate this. So everyone's heard about a cell. A cell is the building mechanism and building block of human bodies. So I have some props. Let's see how this works. Okay. My grad student helped with this morning. Okay. So this is a normal cell. Okay. So it's kind of sphere-like. It's mostly flat, and it looks like an inflated balloon, more or less. It's an inflated glove, a clean glove, I promise. But it's an inflated balloon, right? So this is what most of your cells will look like. And don't fly away. Okay. Now, the lungs are different because the cells in the lungs actually look like this. Okay. They have these really special structures called cilia, which are these finger-like projections away from the cell. And as you can see from this glove compared to that glove, there's now 5 times more surface in the same cell, okay, even though it's the same size, really, more or less. But the fact that it's a different shape helps it a lot because you now have 5 times more ability to exchange oxygen, which is really what the lungs want to do. In addition, these things actually move all of the time. They're like beating, kind of very much like waves. And that in itself is really important because this beating motion gets rid of things like dust particles and debris and helps your lungs get rid of things you don't want. Okay, so this is the environment that we're going to be talking about a lot, is these ciliated respiratory epithelial cells, which make up the lining of our lungs. These cells are the main target for the flu. The flu is caused by influenza viruses, usually influenza A or influenza B virus, that are very closely related. And they infect these ciliated respiratory epithelial cells. Now, by show of hands, who here has heard of the flu?
Oh, well.
Yeah, right. Good. Okay, good. Everyone's listening to me. And by another show of hands, who here has had the flu? Yeah, okay. This is more or less what I expect. Okay, so you all know what I'm talking about, so I don't need to be here, right? I can go. So the flu attacks your respiratory epithelial cells. And what it does is it goes in, okay? It's going to go into here, and the virus is going to start making more of itself. Now, I tell this to my second year students because it's a sentence that I live by. Viruses are obligate intracellular parasites. What that means is that they can only make more of themselves when they're inside that host, okay? And they're fully parasitizing the host, in this case, us. They're using our resources, our food, our proteins to make more of themselves to the complete detriment of their host, okay? So they need to be inside of a cell, and they're using up as much of that cell as possible to their own advantage. They're parasites. So once that virus has made its way into the cell, it's going to make more and more and more copies of itself. Usually, if one virus goes in here, about 100,000 are going to come out. Okay, this is a really efficient process. The virus is really good at doing this. But as you can imagine, this is the same amount of space, right? So as we're making more and more and more virus, eventually you've taken up so much space that the balloon bursts. Okay, I'm not going to put the balloon because that's going to be really loud, but the balloon bursts. And what that does is it kills the cell. It releases a lot of virus to the environment, which is what the virus wants. But as far as we are concerned, that cell is now dead, which means there's a teeny tiny gap in your lungs where oxygen exchange is no longer happening because the place where it was happening is now gone. So you have a little bit of a hole. You also have all of this debris everywhere, okay? So it's kind of like a balloon full of glitter, and now the glitter is all over the neighboring cells in your floor, and there's no getting rid of it because it's stuck to everything, okay? So all of this glitter, somebody needs to come and mop up and get rid of because it's getting in the way of neighboring cells, okay? And this glitter is also a source of nutrients for other things like bacteria that I'm going to tell you about in just a second. Okay, so if we think about this context, when we get the flu as a person, your experience will be, I was at home for like 7 to 10 days, couldn't get out of bed, I felt absolutely terrible, okay? To a point where a lot of people describe this as somebody sitting on their chest because it's so hard to breathe. You feel like you have this massive weight on your lungs. The reason you do is because your lung is now actually full of these micro holes where all of the cells have died. So you actually have a lot less space for oxygen exchange. So, no one's really sitting on top of your lungs, but your lungs are at a severely diminished capacity. Okay, so because we also have less oxygen exchange, you are then also going to have things like muscle aches, because your muscles are actually struggling to get everything that they need to function properly. The other two things that happen are a fever, okay? Almost universally, if you have the flu, you're going to develop a fever, which means your temperature is going to rise. Now, a lot of people find that really uncomfortable, but actually just as a cool thing, there was a new paper out like a month ago that demonstrated that the elevated temperature that happens during a human fever is actually a way to suppress virus replication, okay? So that fever is actually really important for your body to fight this pathogen. So maybe stay away from the ibuprofen for a little bit. I mean, I know it's terrible, but the fever does actually have a purpose. And the last thing, as you can imagine, in a response to any pathogen is that your immune system is going to come around and try to fight this, okay? So you're going to have your immune system going in there, attempting to fight off this virus, and as a consequence, it itself may cause a little bit of damage as well, okay? But at the end of the 7 to 10 days, you will feel better by far and large. Most people describe the flu as a mild to moderate self-limiting disease. Okay, you probably don't feel that when you have it. It does not feel moderate at all, right? But that's what it is. You're very rarely going to make it to the hospital unless you have a significant number of comorbidities, and you will likely get better on your own for the majority of people, right? But you feel better after 7 to 10 days, at least on the surface. So you're likely going back to work, whether you like it or not, or going back to school, probably you'd like that even less. But either way, you're back as a functioning-ish member of society. But that's not actually the reality. inside of your lungs, that recovery is still ongoing, okay? Because those tiny holes that the virus poked are actually still there, okay? So your body needs time to regenerate those cells and fill in the holes. So even if that process has started, it's not completed. So about 7 to 10 days, the holes in your lungs will be filled with these cells, right? So the hole itself is plugged. There is a cell there because your body has regenerated this, but these are not what's supposed to be in your lungs, right? Like they're missing things. They're supposed to look like this. And your cells can actually differentiate, change from this one to that one in a very well orchestrated process that's actually really important for the function of your lungs. But it takes a while, okay? So at 2 weeks, you're going to be about here. And then as time goes, you're going to have one, and then a second cilia, and a third one, and a fourth one, and so on. The process takes about 5 weeks, okay? So even if you feel better after a week, your lungs are not back to capacity for another month after that. Okay, so your cells are doing their thing, trying to grow and get back to normal. So your oxygen capacity is still quite low at that point. So maybe you're better, but not entirely at a molecular level. And there is another thing that's happened. Well, two other things that have happened. I told you your immune system has been a part of this, right? But in an effort to fight the virus, a lot of immune cells actually go in, kill the virus, and then kill themselves. Okay, it's a way that our immune system functions on purpose, and it's an attempt to limit damage. But then it takes a while for really those troops of your immune system to be replenished. So, you know, the front row of the troops have gone in, fought the virus, died valiantly in that effort. It takes a bit of time for the back of the troops to catch up and get back up there. Excuse me. And that takes another more or less similar period of 4 to 5 weeks, right? So between that period of you feeling better and the period of you being at 100%, there's actually this really big 3-week gap. And that's part of the really interesting component. For me, it's one of the main things that we study, which is co-infection. So all of this that I've been telling you about is the virus, right? This is what the virus does. This is what the flu does. But my title was about the flu being more than the flu, right? And this is where my second favorite pathogen comes in. It's called Staphylococcus aureus, or as you hear me say, staph, because I like abbreviating everything. And Staph aureus is a gram-positive pathogen, which is actually something we call an opportunistic pathogen. What that means is that staph lives on us all of the time. I'm going to estimate there's about 80 people here, give or take. So me and the front 2 sets tables, all of us as a third of this room are constantly colonized by Staph aureus. Sorry, Peter, this is the reality. Okay, so Staph aureus lives quite innocuously in your nose or on your skin, okay? And it's part of your microbiota there. It just exists, you're none the wiser. It's doing a few things, but like, you know, nobody knows but your immune system. And maybe your doctor if you've been screened, okay? So it just exists there and it's waiting for an opportunity. It's lurking in the bushes. And when that opportunity presents itself, i.e. your immune system is down because it's just been fighting this virus and the troops haven't been regenerated, those bacteria can move from your nose down towards the rest of your respiratory system, i.e. your lungs. Okay, so staph is there all the time, or it can come from another source or another human, depending on the situation. And then it's found a really nice home. I want to tell you about this home in a second. Okay, but the other thing I want to tell you about Staph aureus is it's also a very versatile pathogen. It can do a lot of different things. And the reason it can do that is because it has a skill to make these things called virulence factors. Now, I spent a bit of time trying to find a good metaphor for virulence factors to explain them. So what happens is the bacteria make these proteins that have a specific function. They're really like remote control bombs Okay, so the bacteria is going to make them, it's going to secrete them out into the environment and direct them to, like, from me to the end of the room. Okay, and once they're there, they're going to explode and they're going to cause damage. And this damage is on purpose because the bacteria can use it to either gain nutrients because they've killed another cell and they can eat this, kill the immune system, which staph does really well, so you're fighting off the army, or both of those things, depending on which pathogen it is. And Staph aureus actually makes several hundred different kinds of bombs that it can do this with, okay? It is really, really skilled at doing this. And I will remind you about my remote control bombs in a few minutes when it gets to talking about my research. Okay, so how do these things come together? Why do we study them? Now, I'm building metaphors here. Since I moved to Victoria, I've actually become a very avid gardener. Okay, so we're going to imagine that our lungs are a small-scale organic farm. Okay, I promise this is going to make sense. Bear with me for a minute. Okay, your lungs are a farm, and really, you as the farmer is doing your level best to continue production. So you have fences that are going to prevent wolves and, you know, deer, if you're in Victoria, from coming in and eating your plants. Okay, on your house, you probably have windows and doors to prevent random people or the weather coming in. You maybe have an electronic system that tells you there's an intruder in here and alerts the police. And maybe if you're like me, you have a pack of dogs that is like constantly circulating around looking for those intruders. Okay. In this case, by the way, the pack of dogs is your immune system. This is on purpose. Okay. So the dogs are a good thing. They're constantly out there sniffing, trying to find something that may be suspect. And if they do, they start barking and alerting you, and then good things happen. Okay. So if your lungs are the small-scale organic farm, when the flu comes around, it does damage. Okay, so we have these holes in our lungs, so we have holes in our fences. Okay, so that means that the deer can come in and eat your plants a little bit unsupervised. Okay, maybe there's been a little bit of a storm and a couple of the windows in your house are broken, so it's a little bit easier for random things to come in. And maybe the alarm that normally takes 3 seconds to start screaming invader now takes 3 minutes, during which time you've been robbed and the person's left, right? And your dogs have valiantly fought these intruders. They've been running around, and they're super tired and sleeping it off in the house, okay? They're still around. They're absolutely fine, I promise, but they're really exhausted. So they're hiding. And this is the environment that Staph aureus comes into after the flu, okay? It's been lurking in the bushes outside of your farm and now goes with, look, there's a hole in that fence. I can go through there and then I can do whatever I want. And really, that's exactly what happens, okay? You have holes in your fence. Your defense system, being your dog pack, is really exhausted and hiding, and nobody notices the second intruder because you're too busy patching up the damage from the first intruder, okay? So when staph comes in, it finds a really nice environment, an environment that's normally not there, okay? So the bacteria love this. Now, a lot of research from me and a number of colleagues around the world have elucidated a lot of the things that happen during this period that I want to tell you about. So staph comes in and a few different things happen. The first one is that the damage that the flu has done has left the environment really sticky. Okay, remember that glitter that exploded everywhere from our dying cells? That glitter is like Velcro. Okay, so the bacteria are coming in and finding an environment and sticking on this Velcro, and now there's no moving them. Okay, so before it was like really slippery and they're like trying to stick around, and now they're on really solid ground. There's Velcro there, and they're like super happy and comfortable. It's no longer difficult to be around. That's part one. Part two, which the bacteria really love, is there's a lot of food. So imagine that this Velcro situation that the bacteria are is in the middle of an all-you-can-eat buffet. Okay, so the bacteria are now nice and comfy on this Velcro, and they're seeing this enormous buffet of lysed cells, proteins, and various other things that they can eat, and no one is stopping them. Okay, so they're on this all-you-can-eat buffet, and they're gorging themselves. The more they eat, of course, the more they grow. The more they grow, the more of their magical remote control bombs they're making. Those remote control bombs are going to go to other parts of the room. They're going to lyse more cells, which means more Velcro, and it means more food for the buffet, right? So it's this constantly amplifying cycle where the bacteria find it easier to stick around. There's way more food, so they're growing way better. And most importantly, there's less of the immune system patrolling, okay? Your lungs have a subset of cells called alveolar macrophages. Macrophages are a really important part of our immune system, and their job is to detect and eat up pathogens, okay? They're going around very much like Pac-Man, okay? Going around and gobbling up everything. That is their job. And alveolar macrophages are basically the exact same thing, except that they're tissue-resident macrophages. They only live in the lungs, and they have very special characteristics for living in the lungs that allow them to do what they do. But flu actually kills alveolar macrophages on purpose so that it weakens your immune response. Even the ones that aren't killed are in a state we call exhaustion, because they've been fighting off the virus for so long, they're no longer able to keep gobbling up other pathogens. So normally when staph encounters alveolar macrophages, it gets eaten up and it's not a problem, okay? None the wiser, you didn't even know it was there. In the environment post-flu, there's basically no alveolar macrophages left. So these bacteria are sitting around, there's no dogs to hound them in the farm, they've made it inside of your house, they found a food stash, and they're making more and more of themselves. And as they do, they're wreaking continuous havoc, breaking more windows, and just generally being really bad. Now, I know that these metaphors are a little bit simplistic, but they're actually based on data. There's a lot of information out there demonstrating that bacteria adhere to or bind better to damaged epithelial cells. There are special bombs that the bacteria make that purposefully release nutrients. Some of them look very similar to viral factors, by the way, and release the same nutrients. And of course, we know the alveolar macrophages are no longer around. So, but what does this mean for us as humans? What it means is you get the flu, you're starting to feel better about day 7, maybe you've gone back to work for a day or 2, and by the time it's day 8 or 9, you're all of a sudden crashing back down again, and you're feeling worse than you did at the start because you now have a secondary infection. Now, many people haven't heard about co-infection because we really don't talk about it that much. But around the world, there is 1 billion flu infections every year. Okay, 1/8 of the human population will get a flu infection every year. Of those people, 500,000 will die around the world. Okay, this is a stat from the World Health Organization that's held true for the last several decades. Of those 500,000, at least 100,000 deaths will be due to bacterial co-infection. Okay, so this is one of the biggest drivers of increased morbidity and mortality associated with influenza. It's one of the main reasons that people make it to a hospital after the flu, because even if you can fight the flu on your own, the co-infection part is much harder. And once you do make it to the hospital, this is when we encounter another challenge. From a clinical perspective, when you go in with a respiratory infection, what's going to happen is your doctor is going to take a chest x-ray, okay, and look at your lungs. That's great. It will likely tell the doctor you have a pneumonia. The problem is, on a chest x-ray, a viral pneumonia, a bacterial pneumonia, or a double pneumonia looks exactly the same. Okay? It is absolutely impossible for your doctor to distinguish one from the other, which means very frequently co-infection is diagnosed a lot later than expected because many doctors don't suspect this. Even if it is diagnosed, it requires culturing of bacteria. So you need to take a sample from somebody's lungs, put it on a petri dish, and grow it in a lab to demonstrate there's bacteria there. That takes 2 days. Okay. During that time, you are in hospital. You'll likely be given antibiotics as a precaution. Okay. But those antibiotics in themselves are a little bit of a problem. I'm going to take you back to the start of my talk when I told you that our lungs are a very special environment. They're really unique, right? They're very outward facing. They do a lot of gas exchange. They're exposed to things all the time. And the majority of movement happens from your lungs to your circulatory system, your blood, and very little happens the other way around outside of carbon dioxide. That's on purpose, okay? You really don't want things leaking in your lungs because that's bad. It also, however, means that if you're given a systemic antibiotic, many of those antibiotics will actually not make it to those respiratory epithelial cells because they physically can't cross that barrier. So even if the drug is effective in the lab and on paper, it's actually not effective in treating your infection because it can't make it to the part where the bacteria live in the first place. So this is really the part that fascinates me. Is this is a relationship that doesn't function as it normally does. It's not just the flu. It's not just the bacteria. It's both of those things together in a very unique respiratory environment. And that's really what my lab has been trying to do for the last several years, both with flu and with SARS-CoV-2, where we're really interested in understanding this three-way relationship. How do different hosts affect the virus? So if I have a mild disease, why do you have a more severe disease? Why does the gentleman over here have no disease at all? Okay. Is there a human factor there that's a little bit different? Is the virus doing something to help the bacteria? We obviously know some parts already happen because things are stickier and there's more nutrients. So that in itself helps the bacteria. But the part I really focus on is, do the bacteria help the virus? Now, the bacteria and the virus really wouldn't be in this relationship very frequently from an evolutionary point of view. Okay, so if we think about selective pressure on the bacteria, it's very unlikely that they're going to make things to help the virus and for no other reason. I totally agree with that. That's logical. But we found through work I've done here and elsewhere that some of these remote control bombs that the bacteria make have functions we know about. They help the bacteria, but they also have other functions. And those other functions help the virus. So some of the work we've been doing has shown that a specific secreted virulence factor, a remote control bomb, let's call it a blue one, okay, when it's on its own, it does a thing, it helps the bacteria. When we're in a co-infection scenario, that blue bomb is still going to help the bacteria, okay? That's what it does. It's what it's designed to do. But it also changes things in the host. And those changes make the host make more virus, okay? So if we have flu here and we've started with 1 and we've made 100,000, if we have flu and bacteria here and our blue bomb, we started with 1 and made 1 million viruses, okay? So you have 10, 15 times more virus being made from each one of those little cells. So when you have several thousand of those infected and 10 times more being made from each one of them, what that means is a lot more virus. And a lot more of this cyclical condition, because more virus means more damage, means the bacteria, they grow more, they make more bombs, that makes more virus, and so on and so forth in this circular scenario that really ends up with us as the host in the hospital in a very serious condition. That was really the part that got me super excited about this field. That was part of my grad degree, and I thought that this blue bomb was really super cool. Not cool if you were the infected person, by the way, just pointing this out, but on the bench in the lab, really super cool. So one of the things I really wanted to do when I started my lab here is take this a little bit further. So one of my super talented grad students actually set up a system in the lab where we have these things. So we have cells from human lungs, and we take a month and we make them from these round guys into these fully differentiated guys that have beating cilia, they produce mucus, they move things around, and they're a full representation of what our respiratory system is. And then we set up co-infections in them. We gave them some virus, we gave them some bacteria. What happens? Well, what happens is the bacteria make this other bomb, a red one this time, that functions in a completely different way. So instead of making it over to the end of the room, it's actually up there on the road. Okay, it's going in a different direction. It's doing a completely different thing. But the end result is the same. It's manipulating you as the host and various pathways inside of your cell that lead to more virus being made. Okay, so this is really cool because we have these multicolored bombs and the bacteria use them all the time. We know about the role of these bombs in the pathogenesis of Staph aureus, and we have for decades. Okay, both of these are very well known, but now they have a completely different role, which manipulates the host and inadvertently helps the virus. And because for me, Staph aureus is the gift that keeps on giving, as I keep telling my students, this is actually something that is not unique to flu. Okay, because when I was working with SARS-CoV-2, we found yet another yellow-colored bomb that does the same thing, but now with SARS-CoV-2. So the yellow-colored bomb comes in, goes inside of your cell, and manipulates the immune system inside that cell. Each one of your cells, by the way, has a mini immune system inside of it. Manipulates that immune system so the cell doesn't know that it's infected, and you now end up with 10 times more SARS-CoV-2. So really, for me, I think this is a representation of the complexity of this environment and how much we don't know. Okay, even if we know a lot about the flu and a lot about staph on their own, there are actually a multitude of interactions we haven't thought about, and there are multiple functions of all of these things that both pathogens make that we're really just beginning to uncover. But I also think that there are ways that this can be useful, because if those interactions are specific or unique to co-infection events, so maybe those blue and red bombs trigger something inside of the host that normally isn't there, that could be a fantastic tool for a diagnostic test further down the line, okay? Or maybe that yellow bomb with SARS-CoV-2 is triggering a specific pathway that normally doesn't happen, and this could be something we can use to design antivirals in the future. So from a clinical perspective, co-infection is really detrimental and is a really serious condition. So if you do get the flu, feel better, and then you feel worse, please go to the hospital, okay? This is important, and get treatment. But it's a difficult condition to treat, right? It's completely undoubtable. But I also think that it's a way for us to understand the system better and understand disease better so that we can be better at fighting it. And the last thing I'm going to tell you before I happily take any questions is that a lot of the data is also demonstrating that co-infection is either less common, less severe, or both in patients who've received a vaccine. So please get your flu shot next year. And on that note, I'll happily take on any questions. In the back.
What point of that process?
Okay, so yeah, so the question is, at what point during that 7 to 10 day period during which you get better, are you no longer infectious? It's a great question. So usually infections stop as soon as symptoms stop. So if you no longer have symptoms, you're no longer producing infectious virus. So probably about a week or so. At the point in time you stop coughing, you're likely not making any more virus and not spreading it to anyone. There may be a little bit of virus left in your system, but it's certainly not enough for you to cough up and spread to others.
Here. Go ahead.
Is there a difference between influenza A and influenza B?
Okay, so that's a great question. So the question is there a difference between influenza A and influenza B viruses in co-infection, and whether we study this? So a lot of the data has come with influenza A viruses, mostly because they've been studied for a lot longer, and co-infection is a really big deal during pandemics, and those are always caused by influenza A viruses. There's a little bit of data showing influenza B viruses as well. As a general rule, however, influenza B infections are much less common. So of that 1 billion I told you about, probably about 10% will be influenza B. So we have a lot less data to play around with. But many of the symptoms in humans from an influenza B infection are very much the same. So imagine that some of the complications will be similar as well.
You say the doctors they prescribe. Why do we take it from the blood and not just?
That's a fantastic question. So the question is, if you're given antibiotics, why do we give them systemically via the blood and not straight into the respiratory system? It's a fantastic question. People have tried. Very frequently, many of those antibiotics are designed to work in the blood and won't actually be in their active state in the lungs. The temperature in the lungs is a little bit different as well. Your body is at 37 degrees Celsius. Sorry, I'm a metric person. But your lungs are probably at about 33, 34, okay, just because they're constantly exposed to air. So some of those molecules simply won't work. But there is a lot of people that are trying to find new formulations of the same antibiotics that can be delivered through things like inhalation or being made into mists. That's definitely a work in progress that can solve a lot of those problems for sure. The biggest problems with those is they need to go via clinical trials again because they're now a completely new formulation, and B, they're usually much more expensive. So depending on the environment you're in and the number of resources that you have, it's a little bit harder to find those in resource limited settings. Yeah, that's a great question. So the question is, can we use this data to really reverse this and use this information to try and fight the virus? So phages are a good idea, and a lot of people are working on phages as alternatives to antibiotics. They still need to be delivered to the lungs, though. For me, one of the easiest ways to use this is actually antibodies. So your immune system will make antibodies to every foreign antigen that exists, right? Same as you did for any of your vaccinations. And if you actually have antibodies targeting some of these blue and red bombs, they're not going to be selected against because it's not a drug that's killing the bacteria. It's really just stopping these proteins from enhancing the virus, and your immune system can do the rest. This is still a thinking process. We're hoping to apply this in the next couple of years, but realistically, that's, for me, the most technically feasible and easiest option. Or finding other mechanisms outside of antibodies that can prevent these proteins from enhancing the virus. Okay, so the follow-up is, are there viral factors that are purposefully not helping the bacteria as a competition scenario? Not that I know of. Now, I know about a lot that do the opposite. So there's a lot of viral factors that target specific molecules that benefit the bacteria. So things like neuraminidase, cleave sugars that the bacteria eats. The other way around, not really, because they're really not in competition with each other. You're going to see a lot of competition between different bacteria because they're going for the same resources, right? The virus is very much in a completely different field, if you will. And most of the virus life cycle is completed inside of a host cell. The bacteria rarely make it inside, so they're not really directly competing for space. And the virus's evolutionary drive is the much bigger evolutionary drive for the virus is actually our host immune system. So there may be mechanisms there through immune mediation, but certainly none that have been elucidated today.
A multifaceted question. I know antivirals often aren't used better from the but if we could distinguish people who might benefit from antivirals, and we use AI-assisted diagnosis, diagnostic procedure, know who has a viral pneumonia bacterial. Do you see advances that might people with a viral pneumonia treated with viral?
Okay, that's a fantastic question. I'll try to paraphrase. Let me know if I don't get this right. But we obviously have antivirals against flu, but those are not frequently given to people because people usually get better on their own. If that is the case, though, can we use this knowledge and AI-driven technology to distinguish between viral pneumonia and co-infection and target antivirals to those patients that need it the most? I think it's a fantastic idea. Certainly, AI in diagnostics has been booming a lot, and I can see how this may be a place where it's well applied. It's hard because chest x-rays are very one-dimensional. So maybe something like a CT would be better to give more data for the AI to do these types of distinctions. The problem with antivirals is they're not great. Now, I did not say this. You did not hear me say this, okay? But so the best antiviral we have against influenza is something called also Tamiflu or Tamiflu, okay? And in a clinical setting, Tamiflu improves symptoms by a day, okay? So you get better a day faster, more or less. And it doesn't actually improve the 4 weeks it takes for your cells to regenerate. So the window of improvement is so small that I don't think it will actually make a big difference to co-infection because the susceptibility is there from factors that are not just the virus. Having said that, I do think that AI has a place for this in diagnostics, and some combination of antivirals and antibacterials at the same time may be highly beneficial, especially to patients at high risk who make it to the hospital. But I think that's definitely a work in progress that should be explored a lot more. I know a number of hospitals in Canada are trialing AI for monitoring patients. I heard a great talk from someone in Toronto who is using AI in the ICU to constantly monitor things like heart rate and breathing patterns of patients, because then you don't need humans to do that, and humans can only do that once every couple of hours, right? And that's been fantastic. So I think the implementation of AI in places like this would be really helpful in clinical management and can certainly decrease a lot of those factors. I want to, yeah. Yeah, so the question is, does antimicrobial resistance increase the risk of co-infection, really? I don't think it necessarily increases the risk of co-infection per se. What it most definitely does do is decrease our ability to treat, okay? So I can't tell you the latest stats in Canada, but I think a solid 60% of Staph aureus isolates are now methicillin-resistant Staph aureus, which means that there's only one drug to treat them, called vancomycin. And there are levels of vancomycin resistance that pop up every once in a while as well. So if we reach a point where those bacteria are fully resistant to everything, then we are actually back to square World War I, where we can't treat those infections. So even if they're not more common, they're more certainly much harder to treat and in a scenario that's already hard to treat anyway. So yes, antimicrobial resistance has a massive role to play in this. And we're seeing more and more infections that are either resistant to many antibiotics or in some cases, all of them. And this is really an ongoing global pandemic that we really need to pay attention to.
What happens when virus mutates? With COVID, we saw a lot of mutations all at once, and that's why it's very difficult for are new-colored bombs created by the bacteria that help the virus in a bigger infection, or will the new strand still work with old, like
Old-colored bombs?
created by the bacteria?
Yeah, that's a great question. So the question is, viruses mutate, right? And when viruses do mutate, Do the bacteria mutate to make new colored bombs, or do the old colored bombs still work the same way? I think it's a lot more of the latter. The old colored bombs are predominantly doing a lot of things to the host. Okay, they're triggering changes in us as humans, not genetic changes, but they're triggering the abundance of proteins here and the types of lipid there. And those are a lot more constant. We evolve a lot slower than viruses do, because we also take much longer to replicate than viruses do. Because for a human, you're looking at about 20 years, and for a virus, you're looking at about 10 hours in culture, right? So it's a bit of a different time scale. So I think it's a lot more that the previous bombs already work. And when we were doing this work with SARS-CoV-2, we were doing at the time the wild type original isolate from Wuhan, and we did alpha, beta, and delta, and really we were seeing the same things. Because I think that the cellular processes that are affected are so fundamental to the virus that really you don't get a selection against them, because the virus needs them to make more of itself. And a lot of the flu things we've seen co-infection with Staph aureus in every single flu pandemic. We see this seasonally. In the lab, we've done this with some pandemic strains, with some seasonal strains, an H1 versus an H3, and they all more or less do the same thing. So I really think the same colored bombs can keep doing the same thing. It's a fantastic question, though. I saw one in the back. Yeah.
Thank you. I was just wondering, when you're talking about, are you able to look at any models that are
No, I really can't. I'm sorry. I mean, I've read a couple of papers on this, and I've heard some really fascinating talks, but I can't tell you the actual AI. Now, the monitoring one, I'm pretty sure is published. It was one of the two major trauma centers in Toronto, and they had done their own AI, by the way. So they weren't using something off the shelf. They built their own. They did their own beta testing, and then they had implemented it for I think about 18 months, and they saw about a 16% drop in mortality in their ICU. So you're talking about fundamental shifts in what we can do, because you're talking about a nurse checking a patient, once every 3 hours, versus a patient being monitored every second of their stay, which means a lot of the small scale changes that may be indicative of, a heart attack or difficulty breathing, anaphylactic shock, so on and so forth, are detected that much faster. Now, it is not a perfect system. It absolutely is not a perfect system, but it is definitely a system that can generate and use a lot more data that can then inform humans. And I know that there are, this is the one that I heard of a couple of years ago. There's obviously a lot more going on around the world where people are trying this in very large scale centers. And I imagine in the next couple of years, we're going to see some very big changes in how clinical data is assessed, just because we'll be better equipped to do it. But on the flip side of this, there is the fact that using AI is actually a massive environmental drain. So and a lot of these AI models are actually using a lot of water and a lot of electricity and a lot of power, which is then impacting climate change. So I don't know how much we're swapping one problem for another. Yeah, it really depends on the model you use, right? But realistically, we need to, as I hopefully told you today, think about all the factors, right? The multifaceted component that is human existence, and the many factors that drive this. Because if we use all the water in California for AI and we can't grow food, it's really not going to benefit us as a species for much longer.
Okay,
Okay.
please join me in thanking Dr. Goncheva.
Thank you all very much.